I'd like to briefly talk about a difference amplifier a little bit for the non-ideal case, but first I need to look at the ideal case. So if we have R1 equals R3 equals, say, 2K, and if R2 is equal to R4 equals 200K, so we've got this condition now where these two resistors and these two resistors are exactly the same. They're perfectly matched, they're perfectly identical. In that condition, the difference amplifier works very well because we've got a differential gain of R2 over R1, which in this case would be 200K over 2K, or 100 volts per volt. And we have RID, the input resistance, looking in this way. Between the two input, I should draw that out here. RID is out here, the differential input resistance, or I should use a little r. And that's just 2R1, which is not as big as we'd like. So that's 2 times 2K, or 4K. And R out, because we have an ideal op amp here, the output resistance is 0. So that's good. And the common mode gain is 0 for this ideal case as well. But what if we have 1% value resistors? That is, they're really plus or minus 1%. And so we might have R1 is equal to 0.99 times 2K, which is 100 or 1980 ohms. It's still really close, right? And R2 is equal to 1.01 times 200K, which would be 202K. And R3 is 1.01. So it maybe this is worst case. So we've got 1.01 times 2K. Oops, I've got too many in there, don't I? So that works out to 2020 ohms. And R4 is 0.99 times 200K. So that's 198K. I think this looks like typical resistors in your kit. It's nothing. I mean, it looks not so crazy. It looks entirely reasonable. So let's find the gain by superposition for VI1 and VI2. So we're finding the gain for VI1 with this one at ground, and then do the opposite. Find the gain for VI2 with VI1 at ground. And so if we do that, so we'll find really V out 1 and V out 2 for those two conditions. Well, V out 1 will be minus R2 over R4, or sorry, R2 over R1 times VI1. And we would have a gain, AI1, I'll call it AI1, A for input 1 of V out 1 over V out 2 of minus 20200. That's that one, divided by this one, 1980. and that gets us minus 102 volts per volt. And V out 2 would be equal to R4 over R4 plus R3 times 1 plus R2 over R1. That's because, remember, for looking at VI2, we have the non-inverting configuration, and so we have that kind of inverting gain due to this branch affecting what the divider sees on this branch. The input is divided here, so we really have a VI plus, which is the VI plus is equal to R4 over R4 plus R3 times VI2, and then that goes into the non-inverting configuration with gain of 1 plus R2 over R1. That's the way we find that whole gain. But so we've got that situation. I made kind of a mess there. Penciling. So if we put those numbers in, we can get a gain of AI2 of 198,000 divided by 198,000 plus 2020 times 1 plus 102. We already have that result from above. And that would be equal to 101.96 volts per volt. That's not the same. We've got some mismatch. It's no longer a perfect difference amplifier. It's not a huge difference, and maybe that's acceptable, but it's no longer perfectly matched the way it is up here. If we can perfectly match these resistors here and here, we've got a great case where we have a perfect differential gain, but just a little bit of mismatch, 1%, which seems perfectly in the normal realm of things, will cause us to start have a mismatch in the gains. And even worse, the common mode gain is no longer equal to 0. That's a perfect case. It's now equal, there's an equation for it in the book, R4 over R4 plus R3 times 1 minus R2 times R3 over R1 times R4. And if we put the numbers in for all these values, we get 0.9899 times 1 minus 1.0408, and that equals minus 0.0404 volts per volt. So the common mode signal is reduced in magnitude. It's smaller than when it went in, but it's no longer infinite. It's no longer perfect, and it will cause us some problems. And in fact, if we find the CMRR, we have 20 log of AD over ACM. Important to use the magnitude of those, which would be equal to 20 log of 102 over 0.0404. It's about it's roughly speaking, it's not quite right, but that's good enough for this case. And we get 68 dB, which is a decent number, but it's not infinite like we had with the perfect matching, and it could be problematic in lots of situations. And the easy or the straightforward way to solve that issue of mismatching these resistors is to use a instrumentation amplifier, which we still have some danger of mismatching in resistors, but it's much reduced, the kind of issues, and there's a number of other advantages. So I'll go over that next. At this point, I don't have any example problems to put in, but if I do, it'll show up next.